Today's notes, we're going to look at linear and angular speed. So suppose a point moves along a circle. Let s be the distance the point travels in t time. So reading that first part, let me draw out what this is talking about. So we have a circle, and on that circle, we have some point. On that circle, your object that's going to be moving, so this little particle is going to be moving around, it's going to move along your circle at some radius. So from the center out, it's going to move at some radius that's going to keep going literally all the way around the circle as much as I need it to. As it travels the distance from one point over to another, so let's say it travels all the way over here to this point, this is still going to be your radius, but it's going to have some angle theta in the middle. What you are trying to calculate is this distance, and I'm kind of overlapping up here at the top. So you're trying to find this distance, which is s. If you think back to what we've already done, that variable s kind of recalls what we've already done before, and especially this length that we're talking about on this arc of your circle is also kind of familiar. If you think back to arc length and area of a sector, we reviewed this already. So what we're really just kind of using here is the arc length to help us with finding our answer. So arc length will help us with identifying our solution here. So that's what linear speed is. Linear speed is pretty much using that arc length to calculate some formula, some value that we're trying to find. Angular speed is a little different, but it still kind of has almost a similar process that we're going to use. So there's my circle, a little different from the first, but it'll work. And we again have some particle, some point that's on that circle. By calculating the angular speed, we're actually going to find a rate at which the central angle is swept by your object that changes its position on that circle. So we're actually going to be using here's my center of my circle. This is my radius. And I have, for instance, this side here, which is also your radius. So you're going to have some theta, and it's going to help you with calculating the rate at which it's actually moving from, let me highlight this, from this point over to the other. So it's actually giving you the rate at which it's moving. So one thing that we're going to do to help us with identifying these solutions a little easier is we're going to use the formula that you should have seen back in probably IPC, maybe physics, maybe even Algebra 1, which is D equals RT. Distance equals rate times time. With the distance equals rate times time, notice how both of these are talking about some type of speed. Well, speed is always a rate. So with that rate, we're going to actually isolate it. So of course we can divide both sides by t. So R, which is your rate, would equal D over t. That's what we're using to find out our answers. So rate is going to equal distance over time, because that's always going to represent some type of speed. So for the linear speed, let me go ahead and zoom in here. For linear speed, we're going to calculate that by using the rate equals the distance times time, over time. Keep in mind though, when you're talking about linear speed and you're looking at that specific arc length up here at the top, the distance normally would be the entire perimeter of some object. But since we have a circle, this is your circumference. So it's going around your circle to talk about your circumference. That's why I related this back to your arc length, because the arc length is just part of your circumference. It's part of your perimeter for your circle. So on this part here, where I have the distance, I'm going to put the actual arc length, which in this case is S. And that's what we labeled it as on this page as well. S equals theta times R. And I'm actually going to do that on this page as well after I rewrite this with green pen. The arc length is calculated by the the radius times theta all over the time. And this is the radius. I don't want you to forget that's your radius because it's coming from that arc length formula, which is S. And we're going to set that equal to the linear speed, which I'm going to note by the letter V. Sometimes you'll see on your homework tests and quizzes, instead of linear speed, you'll see linear velocity. Either way, both of those mean the exact same thing. So this formula we're going to use. If you think back to when we were using the arc length formula, there was a little note I said after I gave you that arc length formula. And that note is that theta needs to be in radians. So the same thing's going to follow because we're literally just using the arc length formula here. So I'm going to add in this last note, which is theta is in radians. So with that being said, I'm going to go ahead and highlight both of these because I don't want you to forget them. So we have our equation here, and we have our little reminder that theta is in radians. Okay, let's talk about angular speed. Okay, so angular speed, again, it's talking about some type of rate. And in that rate, we're going to again use the distance over time. So rate is equal to the distance over some type of time. Okay, well, let's think about the distance. If we look back at this circle, even though we're going from one point to the other, so over from here to here, we're actually going in all of this space, that whole angle. We're going from this side all the way over to this side. It's the entire angle. So what I need to do for my distance is I need to use theta, some angle that's going to go from this side and it's going to sweep over to this side here. So my distance, I'm going to set that equal to your angle, which in this case is theta. And again, this is over time. So to simplify this a bit, there's not really a formula for your angle, it's just theta, and we're going to divide that by time. This is going to be your angular, forgot what I was looking at, your angular speed, or some teachers and some tests might call it velocity. And that we'll note by the letter, we'll use W. And again, since we have that theta, remember, and I'm going to make this little note, theta is in radians. So make sure you make a note that theta needs to be in radians. Okay, so there's of course plenty of different things I could do to help you guys with memorizing this process and these steps. The thing is, if I give you more formulas, it's just going to help you forget them quicker. So what I'm going to do instead is we're going to use dimensional analysis to solve each of these questions. You've seen dimensional analysis back in Algebra 1, back in geometry, back in Algebra 2 for a bit, back in IPC. You've seen it a lot. So instead of having you guys memorize a brand new formula, let's just use dimensional analysis. And with dimensional analysis, that's going to require you to understand some equivalent ratios. So the equivalent ratios that I want to use, or conversions, are going to help you with solving your problems a lot quicker. So for instance, if you have 1 revolution, think about it, 1 revolution. That means if you're looking at some type of circle, a revolution is going to start at one point and it's going to go all the way back around until it gets back to where it started. Well, we've been talking about this for a while. The entire circumference around an entire circle, or the entire distance around a circle, is just 2 pi, which is the same thing as 360 degrees. Remember how I said it's the distance around your circle? Well, that's just the circumference. So I'm going to make this little note. This is your circumference, which is the formula 2 pi r, or you can write it as pi d. All of these mean the same thing. So 1 revolution is just the going around that entire circle, just the distance around it. Okay, so we've talked about all of the different conversions and the different units that we can use. Let's go ahead and use this information that we just talked about, and let's go ahead and find the answer to example 4. Keep in mind, linear speed is discussing the arc length. Angular speed is discussing an angle. So it's going from one point across your circle to another point. Okay, so let's look at the example 4. Example 4 says a ceiling fan with 16-inch blades rotates at 45 RPM. RPM, some of you guys might not know, that's your revolutions, if I could spell it correctly. Revolutions per minute. So that's your revolutions per minute. We need to find the angular speed and the linear speed for this problem. Okay, well, let's try to figure out what these 16-inch blades represent. I know it's 16 inches, but what is that? Well, if you think about a ceiling fan has the center of it, and each of the sides are your blades. So as it goes from the center out, that's the blade of the ceiling fan. So that's your radius. So 16 inches is your radius. So we need to use the angular speed understanding that we have to try to figure out how to get this from RPM, which is revolutions per minute, into radians per second. Remember how I said before that you just need to know dimensional analysis to solve these? This is why. We're going from 45 RPM. And let me actually rewrite RPM as revolutions per minute. We need to change this revolutions per minute, or RPM, into radians per second. Okay, so we just need to do some unit conversions, that's all. Let's start with the numerator, which is the revolutions. We need to change revolutions into radians. Okay, well, let me think. If I want to get my revolutions into radians, let me look back on top. Oh, look, it's in the perfect view. 1 revolution is equal to 2 pi radians. So we're going to write this as 1 revolution and 2 pi radians. When I do that, the revolutions cancel, and the degree, or excuse me, the unit that I want to have in my numerator is radians. Okay, cool. I've done the first part. Now I need to convert this from minutes into seconds. Okay, well, let's use basic conversions that you should know coming into this. Even though I didn't list them out, it's my understanding that you should understand how to get from minutes into seconds. Well, there are 60 seconds in 1 minute, if I can write minute correctly. The minutes in the numerator and denominator are going to cancel. Once you have all of these units that cancel, make sure that you have radians in the numerator and seconds in the denominator. That's what I want to see. So we're going to have 45 times 2 pi radians over 60 seconds. Okay, well, the cool thing is you can definitely solve this by hand. You can definitely do that. It's not too difficult. Or you could use a calculator. Especially since you guys have a brain, let's use your brain right now, and let's go ahead and simplify. So especially if I don't give you a calculator on your test or quiz, you know what to do. So we're going to go ahead and reduce the 2 and 60. 2 divided by 60 is going to give you 1 over 30. And then 45 and 30, you can divide both of them. So I know I can divide both of them by 5. So 45 divided by 5 is going to give me 9. And then 30 divided by 5 is 6. I can reduce this one more time. So I can do both of these by 3. So this will be 3. This will be 2. Okay, let me rewrite what I have with all of this craziness. I have 3 times 1 times pi. So that's just going to give me 3 pi radians over the 2 seconds, because all the other numbers canceled. So that's my answer. I have 3 pi over 2. So 3 pi over 2 radians per second. So that would be my answer. If I ask you to approximate this in decimal form, of course you're going to need to use your calculator. And you can technically use this with any calculator. You can use graphing or scientific. Since I have graphing readily on my laptop, I'm going to go ahead and use the graphing calculator. So we're going to go into a new document. Every time I start this, guys, I'm assuming you've already reset it. Don't push the little button on the back. Go through the steps of hitting option 2, which is my document, and going from there to clear it. So moving on, we're going to go ahead and go into a new document, and we're going to add a calculator. In this calculator, it doesn't matter if your calculator's in degree mode or radians, it's still going to give you the same answer. So for these questions, it doesn't matter which one you have it as. We're going to put in a fraction, and I'm going to type in 3 pi over 2. My approximate decimal, which I'm going to recopy, will be about 4.71239, which I'll approximate for my final answer to be about 4.71. Let me minimize this so you can see it. So I'll have about 4.71, and this will be radians per second. And I'm putting it this way because I'm running out of space on my end, but you could put the same slash that I did before. So like this slash, you can put it here. Same thing. Either way, both of these would be considered a sufficient answer. If I ask you to give me your answer in decimal form, make sure you give me your answer in decimal form. If I ask you to leave it in terms of pi, leave it like this. Leave it in radians per second with that pi. So that's all we're doing. Let's go ahead and look at number 2, which is over linear speed. Okay, with linear speed, it also gives me a unit conversion. It wants you to change it from the revolutions per minute, which it currently is, into inches per second. So let's go ahead and use the knowledge that we have of 45 revolutions per minute and convert this into inches per second. Okay, well, let me think. Okay, well, if I was doing revolutions, the first thing I did before was I went 2 pi radians into 1 revolution. Look at everything that I have for my equivalent ratios. Which of these would be the best thing to use in order to convert from revolutions into inches? Well, the only thing I could see using would be either the circumference, either of these circumference formulas, because they're technically the same, either 2 pi r or pi d. Since we have radius in our problem, let's go ahead and use 2 pi r because 1 revolution is the same as 2 pi radians, 1 revolution is the same as 360, 1 revolution is the same as 2 pi r, which is the circumference, and 1 revolution is the same as pi d. So since all of these are equivalent of each other, we're just going to take that 2 pi r and we're going to substitute it in. The radius we already know is 16 inches. So we're going to have 1 revolution and 2 pi r inches for my circumference. The revolutions are going to cancel, and I'm left with inches in my numerator, which is what I want. And then again, once we have the inches in the numerator, we need to get from minutes into seconds. We've already done this conversion before. 1 minute is equal to 60 seconds. Minutes cancel, and I'm left with my final answer is inches and seconds. All we need to do from here, guys, is simplify. So I'm going to rewrite everything that I have. I have 45 times 2 pi times 16 inches, and we have 60 seconds. Of course, guys, you can easily solve this on your own, but I'm going to go ahead and simplify this with you. Do 1 and 30. We know that 45 over 30 reduced, like we saw at the top, to 3 over 2. And then 8 or 16 divided by 2 is going to give me 8. So all I have in the numerator are 3, 1, and 8. And don't forget that pi, guys. Please don't forget that pi. So that's 24. Let me actually write this in blue. Is going to equal 24 pi inches over, if you look at the denominator, all of the numbers canceled. So we have seconds just in the denominator. So inches and seconds over the denominator. So this would be my answer. And of course, we could put this whole thing over seconds, but especially since you'll probably see answer choices that don't have it as a whole big fraction, this will be okay. Just like we did before, I'm going to get my calculator out and put this in my calculator to see what 24 pi is going to be. Again, it doesn't need to be in degrees or radians. It doesn't matter. So just plug it in. We have 24 pi, and that's going to give you 75.3982, which is approximately 75 point, we'll say 40 inches per second. All I'm doing is I'm rounding it to the nearest tenths or hundredths place, so 2 decimal places. This would be your answer. So keep in mind, guys, this is all we're doing. We're just going from one unit of measure into another. That's all we're doing. I'm going to look at a few more examples with you, and then you guys are going to try some on your own. So let's look at example 5. In example 5, it says a woman is riding a bicycle whose wheels are 30 inches in diameter. If the wheel rotates at 150 RPM, find the speed at which she is traveling in miles per hour. Okay, so the first thing that I notice is we have 30 inches in diameter. So I'm going to make a note that D is going to equal 30 inches. I need to get from 150 revolutions per minute into miles per hour. Okay, let's focus. I like to focus in my numerator first. Let's go from revolutions into miles, just so that way we can get that one done. Okay, let me scroll back up to the top and see what I have. I have 1 revolution is equal to 2 pi radians, which is equal to 360, which is equal to 2 pi r, which is equal to pi d. Well, I could either use 2 pi r or pi d. It's still going to give me the same answer. Since I have the diameter in this problem, I'm going to be a little lazy, and I'm just going to use pi d. So we're going to do pi d, which is 30 inches. And that's going to equal to 1 revolution. So my revolutions are gone. It's cool that I have inches, but I need it in miles. So before I do anything else, I need to convert this from inches into miles. Okay, so let me think. I know I can convert from inches into feet pretty easily. And I know there is a conversion from feet into miles. So let's go ahead and use that. How many inches are in 1 foot? There are 12 inches in 1 foot. Now the fun part. How many feet are in 1 mile? There are 5,280 feet in 1 mile. Now notice that I have just miles in my numerator. That's what I want to see. Right now, if I was to stop, my units would be in miles per minute. I want miles per hour. So the only other thing that I need to do is I need to convert from minutes into hours by doing 60 minutes in 1 hour. Once I do the computation for all of this, I'll be able to get my answer. Keep in mind, guys, if I wanted you to, I would actually have you multiply all of this out. But luckily for you guys, we have a calculator nearby, so we can use that. Keep in mind, guys, though, if I do ask you to simplify this by hand, it's not too far out of sight. You can definitely do this. Okay, so I'm going to multiply this stuff off camera. I'm just going to multiply all of the numerator numbers. So 150 times 30 times 60. So that's going to give me, whoa, that's a big number. We're going to get 4 zeros. So 270,000 pi in miles over 5,280 times 12 times really just a bunch of ones, which isn't going to change my answer, which will give me 63360 hours. Of course, guys, see if you can simplify this. So if I plug this in my calculator, my 270,000 divided by 63360, that's going to give me a simplified fraction of, which you will definitely enjoy, 375 pi over 88, and this is in miles per hour. So if I asked for this as a simplified fraction in pi form, I would definitely want to see this, which I mean might not happen too often. More than not, especially for questions like this, I'll probably just ask you to plug everything in your calculator. So all I'm going to do from here is I'm just going to actually multiply this by pi and get my final answer, which should be about 13.3875. And this is again in miles per hour, which I'll simplify further to 13.39 miles per hour. Both of these would be a sufficient answer, especially for questions that are a bit obnoxious, guys. Unless you're doing a makeup exam, I'll probably ask you to just to give me your decimal form with the calculator. But if I ask you to use a graphing calculator to simplify into fraction form, you can definitely do it. Okay, let's go ahead and look at example 6. And then after example 6, I'll give you guys a couple to try. Okay, so the first thing it says is the circular blade of a saw has a diameter of 7.25 inches and rotates 4,800 revolutions per minute. Find the linear speed of the saw in feet per second as they contact the wood being cut. Okay, so let me label what I have. First thing that I notice is that I do have a diameter, which is 7.25 inches. If I could actually write 25 inches. And it's doing 4,800 revolutions per minute. I need to find the linear speed in feet per second. So down here, let's go ahead and go from 4,800 revolutions per minute into feet per second. I'm giving you a head start. See if you can figure this out before I do it. As I told you guys before, focus with one thing. We're going to focus with the revolutions first. We need this to be in feet. So first thing we're going to do, if I look back at my conversions at the top of the page, I can use 1 revolution will equal pi d again. Since I have the diameter, let's go ahead and use that diameter. So we're going to have pi times 7.25. This is in inches. And it's going to equal to 1 revolution. I now need to get from inches into feet, which is 12 inches are equal to 1 foot. Okay, cool. My numerator has nothing but feet. That's what I want. My denominator has minutes. I need to get this minutes into seconds. So in order to do that, we're going to do 1 minute is equal to 60 seconds. Cross out my minutes, cross out my minutes. Let's zoom out a bit, and we're going to plug all of this in. So let me show you guys what I did for the last problem on my calculator, so that way you have it. I'm going to write it two ways. I'm going to write it in terms of pi, if that looks kind of nice, and then we're going to write it in decimal form for sure. So we're going to take the 4,800, delete, 100, times 7.25, and we're going to keep that as our numerator, so that's going to be 34800, and that's in terms of pi, over 60 times 12, which is too big for me to do in my head for right now. It's going to be 720. This is in feet per second. All I need to do from here is rewrite this as a fraction so I can simplify it. So we're going to have 34800 divided by 720. I'm doing this so that way you can see exactly how I got that decimal. So when you're doing this on tests and quizzes, you can see how I got it in fraction form and how I got it in decimal form, so you don't have any questions. Once I have that, I literally just scroll up, copy it, multiply it by pi, and it'll give me my decimal. So let me go ahead and move this over so that way you guys can see what I've been writing. I have my fraction form, and my approximate decimal will be 151.84, and that's in feet per second. That would be my answer. So hopefully this makes a little bit of sense. As long as you can do unit conversions, guys, you should be good with getting from one unit of measure into the other. So let's go ahead and look at some practice questions that I want you guys to try. This whole page here is nothing but a refresher of arc length and sector area. So this whole page is a review of arc length and sector area. This page is going to be a review of the stuff that we just talked about as far as linear and angular speed is concerned. Right now, I want you to pause the video and do question 13A, so 13A, and question 17. So just 13 part A, and then all of question 17. So go ahead and pause the video right now and do question 13A and all of question 17. So we're first going to look at 13A. So this one was very simple. It was just over angular speed, and you were going from revolutions per minute into radians per minute. So the great thing about this question is once you have it in revolutions per minute and you're getting it into radians, there's really just one conversion you're doing, which is going from radians into revolutions, revolutions into radians. The great thing about minutes is it's already the same denominator that I need. So minutes is what I have, minutes is what I need. So this would be my answer. If I was to write this in decimal form, I'm going to scoot this over and write the approximation. So this would be approximately 6,283.19 radians per minute. So this should be your answer. Go ahead and pause the video again if you haven't already tried, and I want you to do question 17 in its entirety. So with example 17A, I went through everything. I think that was probably the easier of the two questions. You just had to take everything, do the correct transformation or the correct calculations, and it would have given you 9/4 feet per second, which is the same as approximately 7.07 feet per second. So it should be about the same. For question B, however, that one's a little different. So for that question, it's asking you for the radius, and it's giving you this crazy equation here. So whenever you're finding the radius for this, which is going from, as it says in the problem, how far is the person from the center? The person's on the side of the little carousel, and it's going to the center. That's just the radius. So what you had to do is actually calculate so far what you have, which in this case is 6 pi r over 60. And what we're going to do now, since we know the linear speed, which is 3.1 feet per second, we're going to set those equal. So I'm going to do that work over here. We're going to have 6 pi r over 60, and we're going to set that equal to 3.1. Obviously, you're going to have to solve. So the 6 over 60, I can actually reduce this a bit to make this pi r over 10 equals 3.1. We'll multiply both sides by 10. So pi r is going to equal 31. And then from here, we're just going to divide both sides by pi. So let me go ahead and use my calculator. We're going to take that 31, divide it by pi, and we're going to get 9.867. Let me move this over. This will be about, r is going to equal approximately 9.87. And we're going to do that in feet per second. That's your rate. Or excuse me, your radius. So since this is your radius, let me actually write that out before I forget. We now need to figure out how much faster is the rider on the outside going than the rider on the inside. Well, based on what we've solved and what we know, we can actually use the speed for both of these to actually find our answer. So we're going to use a linear speed for the first one, which is 7.07, and the linear speed for the second one, which is 3.1, and we're going to subtract. So down here, we're just going to take 7.07 and we're going to subtract it from 3.1, which is about 3.97. That is the rate in feet per second. That would be my answer. So let me go ahead and zoom out a bit. I think I need to highlight this one as well. And those should be my answers. There's one last thing I want to talk about before we go, and that's question number 12 at the top of the page. Question number 12 is a little different, but it does have an important concept that we need to know, and it's actually talking about an arc length. Keep in mind, this doesn't have anything to do with linear and angular speed. We're officially done, but I want to go through this question because you might see questions like this in the future. Okay, so for question 12, this one says, let me zoom out a bit. Memphis, Tennessee, and New Orleans, Louisiana lie approximately on the same meridian, which is the longitude line. Memphis has a latitude of 35 degrees north, and New Orleans has a latitude of 30 degrees north. Find the distance between these cities if the radius of the Earth is 3,960 miles. Okay, so what this means is you have the Earth. And here's my best kind of way of drawing this. Sorry about my drawing, guys. We have on the same meridian, which is going to be from here all the way down to about here. It's going to be like around the side of your Earth. It's going to come from the center out to one side and the center out to another. In these 2 points, you have Memphis and you have New Orleans. What you need to find is this distance between them. So let me draw this out as a two-dimensional figure because it'll be a lot easier to see that way. So here's your circle, that little slice that I've kind of cut out between Memphis and New Orleans. Here's Memphis, and here is New Orleans. We need to find out what this arc length is. It says that Memphis is at 35 degrees north, and it says that New Orleans is at 30 degrees north. So if we're looking at some kind of circle, the central angle would just be between the 35 degrees and the 30 degrees. Well, 35 minus 30 is just going to give me 5 degrees. That's your angle. So the last thing I need is to actually identify where your radius is. So the radius is 3,960 miles, which is what I need to finish. So the last thing I need to do is actually find out what is this distance going to be between these two cities right here that I'm highlighting in red. Let me actually highlight this in yellow. What's that distance going to be? So right now I want you to pause the video. See if you remember from last class, how are you going to find that arc length right there, the distance between both of those cities? Go ahead and pause the video and find that now. So this is what I have. I first converted, remember this was going from 35 degrees north to 30 degrees north. So that distance from here to here was just 5 degrees. I took that 5 degrees and I immediately transformed this into radians because if you think back to your area, sector area and arc length notes, you have to have your theta in radians. So once I wrote them in radians, so I pretty much just multiplied 5 times pi and divided it by 180, I got pi over 36. So this is the same thing as 5 degrees, but it's in radians. I then took the arc length formula, which is S, and I did R times theta. So I just took the R times theta and got 110 pi miles, which is technically my radian answer. I'm moving this over, and we're going to approximate this in its decimal form, which should be about 345.58 miles. So either of these two would be your answer. Keep in mind, guys, this was just kind of like a bonus question, number 12, with helping you see the distance between two cities. It's very, very similar to what you've already seen with arc length. I just wanted to give you that just to help you. If you have any other questions on any of this stuff, guys, please let me know.